Hi, welcome to my talk When Expectations and Reality Collide in Introductory Physics Labs. My name is Stein. I'm from the Laboratory of Atomic and Solid-State Physics at Cornell University. Just about 2 years ago, I was working in Germany at the Institute for Plasma Physics, and I was working on the heating system of this device shown here to the right, which is called the Stein 7X. It's a stellarator, and it's one of the devices that might, in the near future, give us nuclear fusion. Now, 2 years later, I'm a graduate student again, and just last semester I was TAing student in an Introductory Physics Labs. I want to start my talk with a comparison of the tasks that I was expected to do when I was doing the work at the Institute for Plasma Physics versus what the students were expected to do when they worked in my Introductory Physics Lab. When I arrived at the Institute for Plasma Physics, the first thing I did, I met with my advisor and we tried to establish a research goal for the time I was there. We decided that I will try to come up with a model for the heating of the plasma, and afterwards we defined criteria for suitable evidence, which means if I came up with this model, how would we even know that I'm describing the right thing, that the model makes actually sense that I came up with. We came up with an experiment, we determined the feasibility of this experiment, an experimental design, constructed and tested an apparatus, analyzed the data, evaluated the results, and then we did something that I never expected I would have to do. We analyzed the implications, and if the results are novel, unexpected, and confirmed. I always thought that if you do an experiment, you're kind of done afterwards, but there goes a lot of work into finding out if that experiments that you just did, if you just could have thought a little harder or read more literature and just figured it out, just thinking about it. And eventually I had to present the work to my supervisor. On the other hand, the students that I were TAing, they did not have to come up with their own research goal usually. They were given a goal. For example, a very simple one would be measure the period of this pendulum, and rather than defining their own criteria for suitable evidence, we give them a stopwatch and they just measure the time. Similarly, they don't have to determine if the experiment is feasible. That's done for them. The experimental design is done for them. Constructing and testing of an apparatus, well, yes, sometimes they have to do that, but it's limited to plugging together some cables. Analyze data, yes, students have to do that. Evaluate their results, yes. Analyze implications, if the results are novel, no, that's usually done for students in their lab instructions already. And when they present their work, yes, they might sometimes have to do it, but Carl Weiman, who published this list of criteria that I just went through, would argue that the actual work in presenting is not done by the students, because this last point, number 8, analyze implications of your work and how the work is important. The students usually don't have to present that, they just have to present whatever they did. So as I said, this is not a list that I just came up with to blow my own trumpet. This is a list published by the physicist Carl Weiman in 2015 to compare these tasks that experimental physicists have to do and that we expect from introductory physics students. Now, if we make the reasonable assumptions that we want introductory physics labs to train students to do eventually the work of experimental physicists, wouldn't it make sense to align the list of tasks that experimental physicists have to do as close as possible to the list that introductory physics students have to do? And yes, work is done in that direction, and there is a focus of introductory physics labs is shifting. It's shifting from verifying physics content to developing research and experimental skills. For example, a very simple change that's happening is that rather than asking students to show that the period of a pendulum is independent of its amplitude, many labs now asks, for example, something like, which factors affect the period of a pendulum, which is much more open-ended and which is what I will call experimentation labs in this talk, while the labs that are asked to reinforce the other labs, the traditional labs, I will call the content reinforcement labs, because their goal is usually to reinforce the content that students learn in physics lectures. We are doing similar work at Cornell. I'm working with the Cornell Interdisciplinary Education Research Group. We have physics and biology, and today I'm going to present the work from Natasha Holmes, my PI, our postdoc Emily Smith, and grad students Cole Walsh, Catherine Quinn, and myself. So I was actually lying to you, and the students that I showed you to the right are not students that are working in content reinforcement labs. Those are students working in experimentation labs. And the tasks that they have to do in this relatively non-traditional experimentation lab experience is much more complex than what usually is expected from students in introductory physics labs. So these students sometimes have to establish their own research goal. And if they establish their own research goal, we cannot give them criteria for suitable evidence because we don't know what they're going to investigate in the labs. Similarly, they have to determine if the experiment they come up with is feasible in the just 4 hours that they usually have to finish an experiment. They come up with their own experimental design, construct and test their own apparatus, then again go through the steps of analyzing and evaluating the data and finding out if they found anything new, and sometimes even present their work. Now, as an education researcher, we ask ourselves, after implementing these labs, what impact do these labs have on students? And there has been a lot of research done now. And the first promising finding is that these labs do not hurt the conceptual understanding as measured by exam performance from students. There has been work done by our postdoc, Emily Smith, and she showed that she did a controlled experiment, putting some students in the content reinforcement labs and some students into the experimentation skills labs, and showed that eventually on the final exam there was no statistically significant difference between their scores. My colleague Cole Walsh, one of the graduate students working with us, has measured critical thinking skills as measured by a standardized assessment, the PLIC, and found that in experimentation labs, students' critical thinking skills improve more than they do in content reinforcement labs. The attitudes towards experimental physics to improve, that was work done by Dr. Emily Smith using the E-class survey, where she also found that in these experimentation labs, the scores go up higher. And it engages students in expert-like behaviors during labs, which is a study done by my PI, Natasha Holmes, already in 2015, where she looked at, do students in experimentation labs actually engage in behaviors that experts would do, that experimental physicists would do in their labs. And she found, yes, they do. And the promising result is even that the year afterwards, when you get the students from the study was separating students into experimentation labs and content reinforcement labs. And in the experimentation labs, the students did all these fantastic things of behaving like experimental physicists. But even the semester after, when they were in the same labs again, the students who were previously in the experimentation labs still behaved more expert-like than the students from the content reinforcement labs. Our graduate student, Catherine Quinn, found that the labs allow students to take on different roles. She did cluster analysis and looked at students that looked at how students divide the different tasks they have to do in lab. For example, some students work on laptops, others work on their desktop, others work on paper, writing stuff down, and even others work on equipment. She also found that between those different roles, there's a gender division, and so it happens that men work more on the equipment, while women usually work more on the laptop. This is not necessarily a good finding, but at least what it allows us is that we can now study these roles as they come up in experimental physics and study how different genders assign and work these different roles. And my own work was finding that these open-ended labs also allow students to engage in questionable research practices. Now, I want to spend the rest of my talk clarifying what these questionable research practices are. I want to do this at the example of the pendulum experiment. We gave students an activity and said the goal of this activity is to find out whether the period of the pendulum depends on the angle of the amplitude of the swing. We're testing the model that the period is 2 pi square root L over G. This is the formula for a mathematical pendulum. Usually the way students approach this activity was they measured the pendulum at different degrees. They compared the two measurements at different degrees using a statistical test. And once they've done that, they improve the experiments again. I want to go through 2 groups and their trajectories through the statistical test. First, I want to look at this group over here. The first experiment they did, they found that the two periods at different angles were statistically indistinguishable. And they said, okay, let's increase the number of swings to make our experiment more precise. And after making it more precise, they found that the angles become less distinguishable, more distinguishable. So they said, since our last efforts at showing that the angles should be indistinguishable did not work, we tried a new method. And the new method they tried is just reducing the number of swings again, lengthen the pendulum, thereby effectively making the experiment less precise. And unsurprisingly, they found that the periods were again statistically indistinguishable. The second group here found initially something that the two measurements were distinguishable, implying that the period is dependent on the amplitude. They said, these statistic values are relatively large, which dictates the data is distinguishable, but our intuition and mathematical foundation says that they should be indistinguishable. And they did something to the experiment, and they did eventually find that their statistic value went down, and the values they measured were less distinguishable. Then eventually they added a large angle to the experiment and said, after finding something clearly distinguishable, this coincides with our expectations, which are based upon the mathematical formula for small angle periods of a pendulum. So when I read through these lab notes of these students, I thought there was something fishy about them. First of all, these students here, this group, initially they say, oh, we expect, our expectation is that, or the formula dictates that the two periods should be indistinguishable. They do something to the experiment, and eventually they do become less distinguishable. Then somehow they must have changed their expectations and said, oh, now we expect them to be different, and they find something completely different. This group here is even more blatantly obvious in telling us their intentions. They're saying their efforts were to show that the angles should be indistinguishable, and unsurprisingly, they do eventually show that they are indistinguishable. So I realized these students seem to confirm the expectations that they were having of the experiment. It's not like, it's a little bit, the students were not believing what they're seeing, but seeing what they're believing. And I wanna make a small comment about that group one down here to emphasize what they did. They found these two values here that are distinguishable, and they didn't like that. They said no. So they inflated their uncertainty to make them indistinguishable. Did the statistical test said they're indistinguishable, then they're happy and they go home. So the question that I tried to find out is, why do students engage in questionable research practice? And I did this with the help, or most of the work was actually done by Dr. Smith, and she did interviews with students and looked through the lab notes again and found that students said, what do you believe is the purpose of when we asked them, what do you believe is the purpose of a physics lab? They said, to show in the lab that the equations and concepts discussed in class indeed hold true and can be measured by you. Or another student said, to me, physics labs are meant as a supplement to the lecture and discussion sections. They're meant to reinforce our knowledge of and display some real-world applications of the equations and concepts that we learn in class. These statements were also corroborated by the interviews and video analysis that we did. So these questionable research practices that we see in labs, they are basically manifestations of students' expectations. They want to find something in the labs, and they use questionable research practices to achieve whatever they want to find, so that their results in the end align with the expectations, and the expectations are set by whatever they've learned in class. So obviously, what we don't want to do in the experimentation labs, at least, where the goal is not to reinforce the content, we don't want students to engage in these questionable research practices. So what can we do to mitigate them? One option would be to give students training in responsible conduct of research. Unfortunately, this somehow relies on the assumptions that students don't know that what they're doing is wrong, that they don't know that selectively analyzing their data is wrong, or that inflating the uncertainty is wrong. And our results are rather suggesting that we don't need to train students to responsibly conduct research, but we rather need to reframe the labs. At the moment, students believe that they have to verify and confirm the the equations that we give to them in instructions. But we want students to test if these equations are true, and we want students to behave as if they were doing actual research. So we somehow need to find a way to reframe the labs powerful enough to make students believe that this is what they have to do. And next semester or in the future, we will try to run a controlled experiment with different conditions that do reframe the labs. So far, we have tried to not grade students on correctness of their findings, but that hasn't brought across the message well enough because students still doing H and questionable research practices. So we have thought about grading students on doing positive behaviors, like taking anomalies in their data seriously, but I will report on whatever we find in the future. Okay, I want to end this talk with my personal experience at the grad student in physics education research, because many of you will go into, will have to apply to grad school very soon. And my personal experience so far is that it's less theory driven and it's much more empirical than traditional physics research. The data we have is much richer and allows many analyses and interpretations. Imagine just a video recording of a classroom. You can do an analysis of talk time, you can analyze who talks to whom, you can analyze the content of what students are talking about. There's a lot to find in just one set of data. The social science theories we're using are less powerful and generalizable than the theories that you might be used from to physics. I like this quote that I found. It's by Bill Frist, and it wasn't in the New York Times. It was actually on fixing healthcare under the Obama administration, not on education research or anything. But it's social science, and he said this is not rocket science. Probably implying that it isn't that hard, but I like the answer that Duncan Watts provided. He said, we're much better at rocket science than we are at the problems to do with human behavior. So it has been a transformative experience to do social science research, because it is incredibly hard. And if you're a physicist, and I don't know, it was hard for me to believe that education research can be that hard. Also, doing experiments itself is hard, because you can only do so many experiments during your PhD. I calculated that if you do 1 experiment per semester, which is approximately what you can do in education research, then the frequency of experiments that you can do is about 10 to the minus 7 hertz, which is pretty small to a normal physicist, at least. And ethics have to be considered. You have to make sure that you don't hurt students in your experiments, that it's not as easy as I thought it might be. But physics education research is a growing field in physics. It's a small, inclusive, open, and friendly community. The results are often contradictory to conventional wisdom in teaching physics, and I'm very happy to be part of that community and hopefully improve the education. Well, thank you for your attention, and if there are any questions, let me know.